Okay, so this is the final lecture on the proof of the Kazhdan and Lusztig isomorphism between the equivariant K-theory of the Steinberg variety and the affine Hecke algebra. I had hoped to cover this in one lecture, but it's become two. And when I was preparing this lecture, I had hoped to only need half this lecture to finish off, but it's become the whole lecture. So basically the first half of the lecture will be SL2. And then the second half of the lecture will be the general case. And I won't give all the details of the general case. I won't even give all the details of SL2, but SL2 should be basically believable. And then once you've seen SL2, you should, exactly the same structure applies in the general case. Okay, so just to save a little bit of time, I want to, so here's something I prepared earlier, which is the, just some recollections from last week. There's two bits of notation that I would like to streamline. So this should all be standard except for the stuff in yellow. So B has finitely many orbits on the flag variety script B, mathcal B, and G has finitely many orbits on the product of B with itself. And I want to denote the orbit corresponding to X, OX. So math BB OX. And so if you want to think about this in type in GLN, if I give you two flags, there is a single invariant of these two flags up to GLN conjugacy, which is their relative position, which is a permutation. For example, if their relative position is the identity, then that means they're equal. And if their relative position is the longest element, then this means that they're transverse. So OX denotes flags in relative position X. And I'm sure I've forgotten a bit of finite file group here. So W subscript F always denotes the finite file group. And if you want a typo that will appear a few times in this notes, I sometimes forget to write W sub F. So that's the first bit of notation that I wasn't using last week. And so we have the flag variety, we have its cotangent bundle. The cotangent bundle has a natural map to the nilpotent cone, which is called the Springer resolution. This agrees with the moment map. This is also can be explicitly understood if we describe the flag variety in terms of a flag and a nilpotent element fixed by that flag, in which case this map just assigns the pair to the nilpotent element. We have the fiber product of the Springer resolution with itself over the nilpotent cone. This is the Steinberg variety. And in previous lectures, we've seen that this is the conormal space for the G action on flags times flags. So that means I take the union of the conormal bundles to all the orbits. That's what's written here, the disjoint union. And when I was discussing the conormal space, I pointed out this lovely feature that in a stratification, you're kind of given the impression that smaller strata are less important than larger strata. So for example, if we think about P1, you have the impression that all the action is on the open stratum, and then there's this little point along to the right. And this is not at all the case. The kind of open stratum and the point have equal weight in the theory. And this occurs when we pass to the conormal space. So the conormal space of the P1 stratified by P1 and a point would be the conormal to the open orbit, which is just the open orbit itself, plus the conormal to the identity, which would be the whole cotangent space at the identity. And so we have two pieces which are of equal dimension. And so all of these pieces are of equal dimension, equal to the number of roots. And their closures, which I'll denote big lambda sub X, are the irreducible components of the Steinberg variety, So so the new notation is script O and lambda sub x. And one more pre-prepared slide is this example that we discussed last time, which is, so here's P1 times P1, flag variety times flag variety for SL2. SL2 has 2 orbits on this. If I give you a pair of points in P1, up to SL2 conjugacy, they're either distinct or not, which says that P1 times P1 is the disjoint union of the diagonal and the complement of the diagonal. So this would be O identity OS. And if we take the co-normal to the diagonal, we get exactly the cotangent space of the diagonal. That's a beautiful general fact. And here, if we take the co-normal, this is an open stratum. And so no directions are orthogonal to it, if you will. And so we just get this co-normal is just the stratum itself. And when we close them up, we get the co-tangent space to P1 union the P1 times P1, B times flag variety times flag variety. And these meet along a subvariety of codimension 1 in both, which is P1, the diagonal. And let me just remark that in general, so this is somewhat what one should have in mind in general, but so the components range from the cotangent space of the flag variety, which is the diagonal, and this is kind of the most non-compact component, to the product of the flag variety with itself, which is the most compact. And we see in this example, that's this piece and that's this piece, because W only has 2 elements in this case. W finite only has 2 elements. But in general, these components will be singular, and their intersection pattern is extremely complicated. So it's an unsolved problem to decide when 2 of these components intersect in codimension 1 in general. So for about 15 or so years, people suspected that the answer was given by some kind of Kazhdan and Lusztig combinatorics, and this was disproved by Kashiwara and Saito in a famous paper in 1998. So are there any questions on these pre-prepared slides? I really like something that I believe I read in something that Macpherson wrote about Kottwitz. And he was talking about affine Chibet varieties, and he was saying how their complexity is totally beyond our ability to comprehend, but we still need to be able to kind of spot patterns and see things in this very, very complicated world. And my understanding is that the geometry of the Steinberg variety is similar. We don't expect to fully understand it. And very, very roughly, but this is very rough, is you can think about the kind of complexities of Kazhdan and Lusztig theory as somehow hidden in the complexity of how all these components interact. Okay. So now I will start writing. So last time, we introduced this anti-spherical module. N, which was a tensor product of the affine Hecke algebra So the induction of the sign, the kind of quantization of the sign representation of the finite Hecke algebra to the affine Hecke algebra. And this was isomorphic as a vector space to ZV plus or minus 1 on the character lattice. So remember that chi is the of T. And this isomorphism sends e to the lambda inside here to theta lambda tensor 1. So remember that the affine Hecke algebra has a Bernstein presentation, and in the Bernstein presentation you have this lattice part and this finite part, and performing this induction basically means that the finite part is killed and we're left with this lattice part. And by abuse of notation I denoted this theta lambda. And the other thing that we did last week was, so this finite part has these HS's. It's the finite part is generated by these HS's for S of finite simple reflection. But as often in the theory, we prefer to use a Kazhdan and Lusztig type generator, which is HS plus V. This is a Kazhdan and Lusztig generator. And it's a rule of the kind of subject that often formulas become simpler when you write them in terms of Kazhdan and Lusztig generators. So it's kind of, here we think about this Kazhdan and Lusztig generator as kind of built out of this one, but it's probably, in nature, it's actually probably the other way around, that this thing is built out of this one. And we established the following very important formula for us, which is the action of, so we have S corresponds to a simple root alpha. And we deduce the following formula. Okay, so this formula is very important. And essentially the entire lecture today will be involved with understanding this formula geometrically. And I just want to, perhaps I should have emphasized this last time in case it wasn't clear, but this factor here doesn't look like a priori like an element inside the lattice part, but it's easy to see that this is B inverse minus V theta minus alpha. And this is some close relative of the Weil character formula for SL2. Okay, so we should just think about this expression here. This is a short way of writing this. Okay. So this is what we should kind of think about, this formula as being a formula on the constructible side. And now we want to interpret this in terms of the K-theoretic side. So in terms of the coherent side. And just a kind of side remark is that I think it's in some sense the genius of Lusztig to realize, so when he sees this formula, he was first operating purely on the constructible side, and then he already saw the potential of this formula to have a meaning in K-theory. So this is called Lusztig. So I think I said last time that this part was well known for about 30 odd years and is due to de Mazure and appears in the de Mazure character formula, for example. But things involving the de Mazure character formula look very distant from affine Hecke algebra type things. And so it's kind of remarkable that this gives an action of the affine Hecke algebra. Okay, so I'm about to move to the next slide. Okay, so we want to show that a similar formula to this holds in K-theory. So let's first do a baby version of the calculation. As I've explained a number of times now, the equivariant K-theory of P1 is the same thing as G mod B. And this is the same thing as the B equivariant K-theory of a point, which is Z x plus or minus 1. And this isomorphism sends x to the n inside here over here to what we call O of m. Okay, so the line bundle O of m on P1 has a unique G equivariant structure, and this determines this isomorphism. And we will use this isomorphism from now on without making a big deal of it. So the first claim, which I want to try to convince you is just Weil's character formula for P1 or for SL2. Is that P1 lower star of P2 upper star. So this gives us a map from Kg of P1 and it sends x to the m to x to the m minus x to the m minus 2, all on 1 minus x to the minus 2, which is x to the m plus x to the m minus 2 plus x to the minus n. Okay. And why is that the case? So this is part of a Cartesian square. And this, so we can write this as P2 prime oops. This is the same thing as P2 prime, P1, what am I doing? P2 upper star, P1 prime, lower star by smooth base change. And now another way of phrasing this isomorphism up here is it's just pullback. And so when I push forward here, I get Weil's character formula. And then when I pull back, nothing happens. Okay. So smooth base change plus Weil character formula. I mean, I'm saying Weil character formula, but you could just say, we know how to calculate the global sections of O of M's on P1. Yeah. This is an exercise. I hope we've all done this exercise at some point in our lives. And claim 2, is that if we do something a little bit more fancy, like we go P1 lower star and tensor with O of minus 2, 1. So this is on P1 times P1. Whoops. Okay, so on P1 times P1, it's a standard notation, or on Pn times Pm, it's a standard notation to write O of Mn for the tensor product of the pullback of O of M on the first factor and O of N on the second factor. And I'm using that convention here. Tensored with the pullback of this from Kg of P1. P1 sends X of M to X minus 2 of what we had up here. And this is essentially, so here what I'm doing is I'm pulling back and tensoring with something. So maybe I'll write it down. This is just the projection formula. So P1 lower star of P1 upper star of minus 2. So that's equal to this tensor P2 upper star of blah. And this via the projection formula is X minus 2 times, O of minus 2 tensor P1 lower star. Okay, and we understand this factor from the previous claim, and this just gives us the minus 2. So this is really not very tricky, but I just want to point out that this factor here is looking quite a lot like this factor here for SL2. It's not quite the same, but it's looking pretty similar. Like if we wanted to write this for SL2, this would be 1 minus x to the minus 2. So we have our denominator. And this numerator would be x to the m minus x to the minus m. And so we're slightly off, but it's looking promising. So that was our baby version. And so now I want to move up to n. So I also want to identify n tilde. So remember that we saw that, so n tilde, this is T star of P1 over, so this is the line bundle on P1, the total space of a line bundle on P1. And it's a general fact in K-theory that, so in homology, we know that, for example, any vector bundle is homotopic to its base space, just by scaling the fibers. And the same thing happens in K-theory. And so we get that the Kg times C star, equivariant K-theory of n tilde, so I've explained this a number of times, is the same thing as the of P1. This is via, so if we call this map Q, this is via Q upper star. So via pullback, this is the same thing as, so by before, except now we have the C star along for the ride, times chi. And remember, I mean, I'm saying remember, and I actually didn't fix the power of Z, but that C star acts on n tilde via scaling, so Z squared. So last time I said this acts by scaling by some power of Z, and then I forgot to check which power of Z I needed for later on. So now this is the, I'm sure you were all couldn't bear the anticipation. Okay. So it just acts by scaling the fibers by a power of Z. Okay. And this is and this V parameter here corresponds to the C star action. Okay. So if I have a space and I know it's K-theory, and now I look at the C star equivariant K-theory of the same space for the trivial action, then this just adds a copy of rep of C star. Essentially just given by the character on which C star acts on any object. Okay, so that's my identification, and we set so from now on, unadorned O means O n tilde. So I want to set so this is isomorphic to P1. Okay, so this I went through this very briefly last time, but inside the Steinberg variety of SL2, we have the easy piece, the cotangent bundle of T star P1, and the tricky piece, which is P1 times P1. And I said one should think about coherent sheaves supported on the T star of P1 as being like diagonal matrices. And now we're creating this off-diagonal element, this QS, and this is supported on this piece inside the Steinberg variety. And the claim, the rough claim, is that convolution with this QS corresponds to multiplication by BS. So that this guy is something like a Kazhdan and Lusztig generator. Okay. And we'll see that up to a sign and a power of V, it is Kazhdan and Lusztig generator. It acts the same way as the Kazhdan and Lusztig generator. Okay, so what do we want to do? We want to calculate how this acts, i.e., we want to take O of M on, so this will be on n tilde, so I'm allowed not to adorn it. We want to pull it back. So my diagram is now the following. I have so this is just another picture of this situation. So here's n tilde tensor n tilde. And so inside this, we can kind of think about the Steinberg as sitting but this picture is not great because the two components would be kind of, this would be the cotangent bundle of P1 that maps isomorphically down onto each component. This is the diagonal. But here we have this interesting piece that's the same dimension as this piece, which is P1 times P1. And what we want to calculate is we want to start with a sheaf on here. We want to pull it back to here. We want to convolve with, we want to tensor product with QS. And now we want to project back down and see what class in K-theory we get. So we should take QS tensored with this. Note that we should, in general, be very we should be very careful with this tensor product in general. But this is a vector bundle. I mean, even a line bundle. We pull it back; it stays a line bundle. Here we're tensoring with a line bundle, and so we don't really need to worry too much. And take the push forward. And we want to know what this is in K-theory. And the first claim is that this thing this agrees with the following, and this is claim 1, which is that it is what we saw in the P1 calculation, so x to the m minus x to the minus m minus 2 over 1 minus x times the class of the So in this picture, we start with something here, we pull it back, and so it's a vector bundle here, a line bundle here, but we tensor with something that's just supported here, and we push forward, and we get something that's just supported here. And the claim is that it's the extension to everything of O of minus 2 on the 0 section. And I'll leave it as an exercise to prove this claim. So, but I'll give you a hint as to how to show it. It's really not difficult. So exercise. So if we have E on Y, a vector bundle, a vector bundle, and imagine that. So if you're new to algebraic geometry, I would recommend you do this exercise. It's really not difficult, but if we have F on Y quasi-coherent, and G on Y locally free, then there's two things that we can do. We could, if an I denotes the inclusion of the zero section, there's two things that we could do. We could take I lower star of G and tensor it with pi upper star, sorry, I lower star of F, and tensor it with pi upper star of G. So that's kind of doing things on E, or we could do things on Y and I guess another point of this exercise is that, I mean, this is a vector bundle, this is a vector bundle, and so I don't have to worry about tors. And now the second part of the exercise is to use A applied to P1 times P1 embedded inside n tilde times n tilde to deduce claim 1. So the yeah, essentially all I'm saying is that in this bit of the calculation, the only thing that happens is based on P1. There's nothing cotangent bundle coming into this calculation whatsoever. Okay. Any questions? So let me copy this formula here. And go to the next slide. So what do we need to do? So we've written our basis of this space is given by line bundles. And this is not a line bundle, this is supported on the zero section. And so basically we need to resolve this by line bundles or vector bundles in order to express this in K-theory, in our basis. So now comes a useful basic technique. So let me apologize to the more experienced algebraic geometers in the audience. I'm going over this stuff carefully, largely for the benefit of students. So we have a vector bundle as before. So and imagine that we want to understand coherent sheaves on V. And that's exactly what that's exactly our situation here. We have our n tilde, which is a vector bundle. This is a coherent sheaf on it, and we would like to understand it in terms of line bundles. And so we have an equivalence of categories, coherent sheaves or quasi-coherent on total space of V. So a vector bundle is locally just looks like some base times an affine space. And we can understand coherent sheaves on an affine space either as being coherent sheaves on an affine space or as being modules over its global sections. And this is essentially a relative version of this. So quasi-coherent sheaves on the total space of V are the same thing as sheaves, quasi-coherent sheaves of modules over Q lower star of the structure sheaf on V. And this is isomorphic to, so this is the thing that makes the kind of vector bundle case. So this general statement will be true for any affine morphism. But in the particular case of a vector bundle, we can write this rather nicely as the symmetric algebra of the dual vector space. Okay. This is just a relative version of the fact that functions on a vector space, regular functions on a vector space, is the same thing as the symmetric algebra of the dual of that vector space. So that's our useful basic technique. So in our setting, so remember that n tilde is the cotangent bundle of P1, is the line bundle associated to O of minus 2. So hence, so this is our V, and it's mapping over P1, which is our Y, and hence sim of V dual is just O plus. So this is a line bundle. So sim just means take the direct sum of all the tensor powers of my line bundle. Okay, so we're looking at sheaves of modules over this this sheaf of algebras. And notice that we have this C star hanging around. So C star acts here as Z squared. And this piece here is the dual space, and so here it acts as Z minus 2. And so we conclude that we have an exact sequence. Essentially, one can think locally. This is just a polynomial ring in one variable. And what I want to imitate is k of x goes to k of x by a multiplication by x goes to k. But there might be some global twisting, and this business above, this useful basic technique, tells me what this global twisting might be or is. And so we have an exact sequence, which is the n, sorry, O of n tilde, and here we have a 2, I lower star of O of P1. And here we have to keep our, so this is a perfectly good map of coherent sheaves on the total space of the cotangent bundle. But in order to make this a map of equivariant sheaves, we need to add a -2 here. And hence we have an exact sequence. And so this tells us, if we tensor product with O of -2, this tells us that in K theory, I lower star of O of P1, this class is simply O of -2 minus V2 O of O. Okay. So if we plug this formula into what we had before, I'll just so this was what O of lambda went to, or O of m went to this, but now we can rewrite this as times this thing. Okay, so now we can, if we rewrite this in terms of x's and y's, we get, and I'll change the order, we get x to the -2 minus v inverse times x to the m minus x to the -2 minus 2. Okay. Now this should be compared with the formula that we want up here. And now I will leave, so we have a lot of ingredients that look very similar on both sides, and I'll leave it as an exercise to check that if we send theta to the m to x to the n minus 1, this intertwines the action of Bs and some multiple of this, which is minus v times the class of Qs, convolution with this. Okay, and this is great because now we have two modules which are isomorphic as vector spaces, and now we've fixed an isomorphism such that the two operators act in the same way, and so it's looking very like these two things are isomorphic. Maybe it's a nice exercise at this point to prove that both modules are faithful, and so that we're done. Okay. So now we will have a 7-minute break or an 8-minute break. So I'll start again at 10:05. And I will go through the structure of the proof in general, which, and I've tried to explain the proof for SL2 in such a way that the general case follows the same structure. One final thing before the break, what we're doing here, so this is a general and very useful thing here. This is an instance of so-called causal resolution of zero section. So see you at 10:05.
Sorry, when you said faithful, which modules faithful? Or which algebra?
So we have the anti-spherical module for the affine Hecke algebra. And we have the, so the first claim is that that module is faithful. And the second claim is that, that the K-theory of the cotangent bundle is also faithful as a module over the K-theory of the Steinberg.
But aren't you sending like all these different H sub S's to the same B? And
no. No, it's here the action really depends on, so this is for an S, for S, which is S alpha.
I guess still kind of concerned by something. Is it like this anti-spherical module like smaller than the affine Hecke algebra in some sense?
Yes, it's much smaller. But it's still, the claim is that it's still a faithful module.
Okay. Okay.
Roughly speaking, so is it useful for me to explain the argument briefly?
That would be useful for me, but.
So I'm very happy to. So, so for the, so let's just do one, because they're essentially, the argument in both cases is essentially identical. So let's just do the case of the affine Hecke algebra. So the affine Hecke algebra has a basis given by finite HW and lattice part times lattice part. And what the lattice part does is it just kind of moves us around in this lattice. And what the Hecke algebra part does is it basically acts as a simple reflection. It acts by, it does some crazy stuff, but roughly speaking, what it does is it acts like that element of the Weil group acts with many other terms. And so now let's, for example, see if the longest element is involved in, so we take some expression and we want to say that if it acts by 0, then it's 0. And let's first argue that the coefficient of the longest element is 0. So the point is that if we go to some weight that's like extremely dominant, and we act, and we get something that's, we get any term that's W0 of that weight, there's no way that something that wasn't W0 could have done that. And then, the argument is similar just by induction on the length of the Coxeter group.
Okay, cool.
just back on Tony's question. So it's very common, for example, to take the trivial representation of a subgroup, induce it to the whole group, and for this representation to be faithful. I mean, you know, sometimes it happens, sometimes it doesn't, but this is possible, and that's some analogous situation that's happening for us here. Okay, so we want to, now the general case. And I just want to emphasize, whoops. That this piece here is kind of, in general, comes from, or push. The P1, and this comes from a causal resolution. And so at the end of the day, it's not a super complicated. It's not super complicated what's going on. So I just want to briefly recall the relative tangent and cotangent bundle. So we have E, Z to Y smooth, or a submersion. And you should think that this just means like a C infinity vibration. So and so a picture of it looks something like, here we have Y, and here we have Z, and then we have all these fibers that are all isomorphic, at least as differential manifolds in the differential geometric setting. And we have two exact sequences. So we can take we can set T Z over Y to be the kernel of the differential of our map F from the cotangent bundle of Z, sorry, from the tangent bundle of Z to the tangent bundle of Y. And then we have an exact sequence so we have a short exact sequence. And roughly speaking, I mean, not only roughly speaking, like this is literally what's going on. T Z over Y is the, so here we have a fiber. And then Tz over Y consists of vectors which are tangent to the fibers. And dually, we have the cotangent bundle. Remember, you can, it's kind of, tangent vectors are functorial, cotangent vectors are contravariant. sorry, it should be pi upper star. Okay, and you can think about elements in this. So this is the relative cotangent bundle.
Is that an F upper star?
Yes. This is the relative cotangent bundle, and you can think about this as being vectors which are covectors perpendicular to fibers. I.e., this is the I'm getting confused. I want to say it's the vectors that pair with any tangent vector to be zero. Why am I getting confused? Anyway. No, so this is just false, no? I should think about, sorry, I think this is wrong. Like the things that are pair with any, this is the things that you should think about as being perpendicular to the fibers. These are the covectors. So these are exactly the covectors that come from below, i.e. they're the things that kind of point away from the fibers. And then this quotient you still think about as covectors being as covectors that are somehow along the fibers. So in the presence of a metric, both of these sequences split. Okay, so this is wrong in the notes. So in our setting, we have B, the variety of Borel subalgebras. So traditionally we think about this as being G mod B, but I think in the context of the Steinberg variety, it's better to think about it as not being, so once we choose a B, this becomes G mod B, but it's better to think about it as just being a variety parameterizing all Borel subalgebras without a specific choice of base point. And then this maps down to BS. So this is variety of parabolic subalgebras. Of type S down to G mod. This is a minimal parabolic, and this is a P1 fibration. So every, so given a Borel subalgebra, we can uniquely turn it into a parabolic subalgebra of type S, and there's P1 ways of doing such a thing. Like for GLN, this would be just a flag and a flag missing a step at the ith piece. And this map is just throwing away the step at the ith piece. And so we have our picture similarly from before. And then we have these P1 fibers. I'm going to call this map pi S. And then we have one of the most important Cartesian diagrams in geometric representation theory, I would say, very basic, is the following, so fundamental Cartesian diagram. So the fiber product is pairs of Borel subalgebras which lie in the same parabolic subalgebra of type S. So this means this is exactly what we're denoting OS bar. So the fiber product is the closure of Borel subalgebras in relative position S. And these are all so all maps are P1 fibrations. And in our baby example before, we had this diagram of P1, P1 point, and P1 times P1 playing a crucial role. And this is the analog of that diagram in general. And we identify and then the kind of analog of baby claim from before is that if we look at, so here we have P2, P1, P2. This sends e to the lambda to e to the lambda minus e to the minus lambda, whoops, to s of lambda minus alpha. And I always, whenever I write S and alpha, I mean alpha corresponds to the simple root S. And again, this is simply an instance of the Weil character formula. You can check this claim after pulling back to a single Borel inside here, in which case we have a P1, and that proves it. So that gives our first kind of piece of the puzzle. Now I want to describe a something that's the kind of cotangent version of this fundamental diagram. And this is really nice. So down here we have BS, B, B, and OS. So this is our Cartesian diagram from before. And now up here, we can put the cotangent bundle of BS. And I want to consider NS, which is, so if this map we denoted pi s, which is pi s upper star of the cotangent bundle. And so down here, so this cotangent bundle here is the set of parabolic subalgebras of type S together with X, such that X is in the nil radical of P. And we have P of type X. So when we pull that back to B, what we get is Bx such that X is in the nil radical of pi s of B. And when we take fiber products, we get something. So we'll decide what the something is in a second. So let us do so. So this is the set of pairs B, B prime X, such that B and B prime are in relative position S. So that's saying that they project the same parabolic subalgebra here, are in relative position S or identity. And then the second condition is that X is in the nil radical of pi s of B, which is the same thing as the nil radical of pi s B prime. But if we ask that B and B prime are in relative position S, then this is precisely the conormal bundle to that orbit in B times B. And so this question mark is lambda S. So we have this big Cartesian cube and so what I was saying before is that in general, these components are, for example, not smooth and very complicated. And somehow the thing that allows us to perform this calculation is that in the particular case of simple reflections, these are nice things. And now the and we define QS to be So let's call this Q. Q upper star of the so this is relative one form. Second projection. So this is the analog of O of minus 2, 0 from before. And remember when we did SL2, the first bit of our calculation was just to say that even though we do something kind of up here, actually it's determined by something down here. And the same thing happens here as earlier. If we take P2 lower star of QS tensored P1 upper star of O of lambda, this is e to the lambda minus e to the this class that kind of comes from P1 times, and before we had the thing supported on the 0 section, here we have I lower star O of n tilde minus alpha. So here we had minus 2, now we get minus alpha. And if you can do the exercise from before, then this is essentially the same calculation. And to calculate, so are there any questions here? I'm aware that this is rather kind of heavy in it. Yeah, prob. So I'll just look at the chat. Should that be bar? Yes. Don't hesitate just to ask also if you okay. Okay, so it remains to express, sorry, this should be NS. So NS is the kind of analog of P1 from before. So NS is a vector subbundle inside the cotangent bundle. These are the covectors that come from BS, and it remains to express in line bundles. And as before, we do this via a causal resolution. are all n tilde instead. Yes. Any more issues with this diagram? And this is a curly B. Okay, so it's just nice to think, what would this diagram, just for fun, let's think what would this diagram be for SL2? So these spaces are of course P1, and this space is the variety of Borel subalgebras of type S, but there's only one, namely SL2. So this is a point, and this is P1 times P1. This is the cotangent variety of a point, so it's a point. This is the pullback of this square. So it's a zero-dimensional vector bundle on a point. I pull back, so this is just B. This is just B, and this is just B times B. Sorry. Yeah, this is B times BB. Okay. So now I'll just go over the causal resolution briefly, and then I'll stop for today. So we, again, so we fix, so we have a short exact sequence. Of B modules, where we have G mod B goes to G mod PS. So G is a B module, and mathfrak B is a B submodule. And so I have this short exact sequence. And if we pass to associated vector bundles, what we get, so the tangent space of the tangent space of the group G at the identity is the Lie algebra of G. And similarly, the tangent space of G mod B at B is mathfrak G mod mathfrak B. And so here we get the tangent bundle G mod B. And here we get pi s upper star of the tangent bundle of G mod PS. So this is isomorphic to B. This is isomorphic to BS. So I said that at the moment I prefer to think about B and BS as being varieties of Borel subalgebras and varieties of parabolic subalgebras, etc. but I couldn't work out a nice way of making this argument without fixing a b. That's what I'm doing here. And this b acts on this guy just with a single character, and our conventions are that this, I mean, to be honest, I got horribly confused yesterday about whether this should be plus or minus alpha, but I think it should be alpha. So this is the line. So now if we pass to, so this is like, we have a vector space. And we have a one-dimensional subspace L. And if we pass to symmetric algebras, then we get that the symmetric algebra on T of G mod B surjects onto the symmetric algebra of G mod B. And then here we so this is a vector bundle version. So we get a short exact sequence. This is a vector bundle version of k x1 to xn, goes via multiplication by xn to k x1 to the xn with quotient x1 to the x minus 1. Okay, so it's a vector bundle version of the causal resolution for a codimension 1 subspace, which is exactly what NS is in, like N tilde S is inside the cotangent bundle. And so what we get, so this gives us the structure sheaf of the cotangent bundle, goes via the structure sheaf of the cotangent bundle, alpha, onto the structure sheaf of NS tilde. And then when we take into account C star actions as before, we get b to the minus 2, b to the minus 2. Okay, and the result is that this class that we wanted to know from before so now when we plug this into this business up here, we get that lambda maps to this, which maps to and again, check that something like theta lambda maps to e to the lambda plus or minus rho. I can't remember which one it is. Intertwines the action of Bs and minus V and convolution with this class. And then I'll just leave it as an exercise. Show that n, respectively, so you'll really need these formulas that we've just established. Faithful modules. And we deduce the Kazhdan and Lusztig theorem. Which is the fact that okay, so next week, we'll start to explain. So what we want to do is so Bezrukavnikov's equivalence is a categorical version of this. And what we want to do is essentially follow the same strategy of proof, but even to match up. So now we need to match the anti-spherical category with coherent sheaves on the Springer resolution. And so that isomorphism of vector spaces for us was easy. You know, these are just both essentially vector spaces of the same dimension. But now we need to establish an equivalence of categories, and that's the Arkhipov-Bezrukavnikov theorem that we will spend some time on. I'm guessing, I seem to always underestimate, so I definitely think that we'll be spending a few weeks on that. Probably next week, I'll start with just recalling some things from Emily's informal Friday seminar concerning Gates-Gree central functors, and we will discuss a very simple example of this for SL2 that's very beautiful, which Emily and I did together a few days ago or a week ago or so.
One question I had was, can you try to do the same thing with the trivial module instead of the sign representation? Awesome
question. So you get formulas in the spherical module that look a little bit different. So they're not, it's like the really nice thing about the antispherical module is we just get something that comes from push-pull times something that comes from another class. And in the spherical module, we get kind of 4 pieces. And the explanation is in fact that the spherical module is those coherent sheaves that are supported on the 0 section. Mm-hmm. So we could redo this whole business with coherent sheaves supported on the 0 section. And we would see, it's a little bit more complicated, but we would see the same formulas. And this reflects the fact, so push forward gives you an inclusion of the spherical module inside the antispherical module. Sorry, push forward. So certainly coherent sheaves on the zero section, K-theory of coherent sheaves on the zero section, has a map to K-theory of coherent sheaves on the Springer resolution. And it turns out that this is an embedding. And on the other side of Langlands duality, if you want, this is a very simple fact that you can embed the spherical module inside the antispherical module.
Okay. But yeah, so I don't see that at the level of finite Hecke algebras, but you're saying that for the affine ones, there actually is an embedding?
Yeah, it's yeah, it's totally not non-obvious in some sense. And this is another thing that Lusztig noticed. Is there a decent way of seeing it? Are you familiar with the picture of the antispherical module via kind of dominant alcoves rather than lattice?
No, sorry.
Yeah, another way you can see it is it's closely related to Weil's character formula. So Weil's character formula says that something anti-symmetric and something symmetric are closely related. And that's reflected in this relationship between the spherical and the antispherical module.
Okay, cool, thanks.
I might say a few words about that next time. But definitely the embedding of spherical inside, and it goes the other way too. You can embed spherical, antispherical inside spherical, and this is a recurring theme in the theory and very important.
Mm-hmm.